okay, because we are making estimates. But the points that I chose was 23 and 460 and 2 and 40, okay? So my slope then 460 minus 40, and that is in newtons, because everything that's rise, centripetal force is in newtons. So I'm going to put even my unit right there on the top. Divided by 23 minus 2 meters squared per second squared, okay, because my units are meters squared per second squared. That gave me 20 newtons per meter squared per second squared. Do you want me to zoom in on that? I just see somebody squinting, I can zoom on. If you have like 19 point something or 20 point something or a little bit different, that's okay. But like what kinds of answers did you have? I see lots of you erasing. Was it kind of? No, okay. Yeah, that's fine. Yep. Okay. Good. So can I move forward? Or, yeah? Okay. So now we're going to, okay. So now we're going to take that data. So we from our graph, we got about whatever you had, like 21 or 20. Let's just use 20 so that we all have the same calculations for right now. Okay, so our answer, we said slope was 20 newtons per meter squared per second squared. Okay, now listen carefully. I'm going to take, oh, am I videotaping? Yeah, I am. Okay, good. What I'm going to do is look at this. I have two things where it says slope equals something and slope equals something. Look, slope equals this and slope equals this. For this example, both are true, yes? So I'm going to take this and go m over r is equal to 20 newtons per meter squared per second squared. Because if slope equals this and slope equals this, I can make them equal each other. Yes? Because look, what are we trying to find? We are trying to find out mass, which is m, so this is that's what we're trying to find out. And in this question, we were just told r. Okay? So now I can insert this information for this variable and solve for m. But see how I needed to use my data, my slope, but I also needed to use my physics formula to figure out what slope was, you know? So there's multiple steps. Oh, it's so exciting, right? Okay? So let's use that radius now and solve for slope. Have you already done that? Did you get it too excited? You already did it, didn't you? Yeah. Okay. So so if we rearrange, we know that m is equal to r times by 20 newtons per meter squared, second squared. And we know that r is equal to 1.15 meters, so times by 20 newtons per meter squared seconds squared. Okay, now watch this. Watch this. This is why units are important. Look it, I can cross off meters here and the square root of the meters there. So I'm left with, okay, my mass is, what's the value there? Like 23, right? Yeah. Okay. So 23 newtons per meters per second squared, which is a unit breakdown of kilograms. That is what a kilogram can be represented like that. So then we can summarize and say 23 kilograms. Or you can just know that when you're using newtons and meters per second, that your mass will always be kilograms, not grams, kilograms. Yeah. That's just the conventional unit that is used in those formulas. Okay? So, we did it! Hooray!
Just that way I guess you can see the cross.
Okay, move on. Next example. So now we can kind of rule with it a little bit more, that we have our steps laid out for us, so you can have that step sheet beside you so that we can kind of go through it. Okay, so let's read this next example. During a NASA test, the velocity of the rocket is measured at different heights from the ground as it is being launched. The following information was recorded. So we have our displacement, and then we have velocity. Okay, so it says, identify the manipulating and the responding variable. So based on the description of the experiment, or whatever's being measured, what is being changed by the person that's in control? The velocity is, it's your displacement. So it's like, when it says the velocity is measured, whatever is measured, that's the result.
Is that your manipulated one? Like the displacement?
Yes. So our displacement then has to be our x, because that's what we can change. Like, we are changing how far the rocket goes. It's kind of hard because you're kind of changing both. But it's, since the velocity is the one that is measured, that's the result. You see what I'm saying? So it's like whatever is your result is your y. Check. A is done. Okay? Determine the equation that is used to describe this situation. If you plotted the x and y variables as is, sketch the shape of the graph you would expect to see. Okay, so what we're going to do, yes, take out your data sheet. Now let's think to ourselves here. As I increase in regular increments of displacement, I'm increasing in my velocity. What type of motion is going on with this rocket, would you say? Is it a uniform motion or an accelerated motion? It is accelerating. So we need to look at our acceleration formulas under our kinematics unit. So we think, okay, what involves velocity and displacement at the same time? We can assume initial velocity is 0. And we'll need acceleration too. Very right. Very good. So let's write that down. So we have our VF squared is equal to VI squared plus 2AD. So now what's our next step? We identified x and y. We found our physics formula. What's our next step? To rearrange to make it a y equals. So if this needs to be our y, so we need to rearrange this formula so all it is VF equals stuff. Okay, so that's our step 3. Now, we can cross this off initially and say that's 0 because we know VI is 0, so that makes our life a little easier. Okay, so let's rearrange. What's the one step we have to do to rearrange? We just have to square root, and so that's nice. So it is VF is equal to the square root of 2AD. Okay, so now we're just going to stop for a moment and look at this, okay? What is the relationship between y and the x variable? So here is our y, VF, and here is our x, okay? Yeah, y is, I would use the word proportional, yep, is proportional to the square root of the x value. Okay, so now we can look at our graphs and see, okay, well, what would we expect what kind of a shape would we expect to see if we plotted that y and that x value? So then let's do a little sketch. Because we don't want to take all that time to plot it out on our diploma. So sometimes we draw a sketch. Okay? So what kind of a sketch would it be? What would we call it? An inverse or parabolic around the x-axis, right? It's this one. That's its relationship. So if we were to sketch it, we should see something like that, right? Okay, but we need to make it a straight line. So next, Steve says, identify what variables need to be plotted to produce a straight line graph. Plot this data, okay? So what do we need to do to the graph, to the x variable to make it straight? Square root all my x values. So I would go back up to here, and I would maybe even make a little another table for myself or something, where every time I put a value in here, I'm going to square root it. Now, don't do that right now. I'm going to show you something. Well, you could if you wanted to. It's fine. I'm going to show you how to plot this in your calculator. Okay? And how to do a linear regression on your calculator. Oh, I can't because I have no batteries. Can I borrow somebody's to do an example? Okay. So, I'm going to... Can you see me? Can you see me? Hi.
Lane, I have a calculator and like changed all the settings and stuff.
That's too bad for you.
Because you restarted it.
Well, you have to clear it. Clear the memory, probably?
Yeah.
Okay, well, just let in a minute, okay? So what you can do is hit the stat button. You're like, okay, stat. Press enter for edit. Okay, you should see it says L1, L2, L3. Yes? Okay. So L1 is default, usually the X, and L2 is default the Y. You can change it if you want to, but it's just easier if you make L1 the X and L2 the Y. So in L1, you can write down square root 25, which you just know, and then arrow down. Square root 50, arrow down. So then in this column, you put in all of the data so that you're not doing it twice. You know what I'm saying? You don't have to write it down on there. You can just do it once in your calculator. Okay, so when you've done the X, column over to L2 and put in the data for Y. Okay, so you entered it into both lines? Yes? Okay. So now, what you can do is you can graph that. So you can see the graph. Have you done graphing much in your classes? In math class? Yeah? Okay, so you need to set your windows as well. So let's set our windows for this. So use your windows for your X, 15, oops, and 2. And for our y, we'll use 0, 110 so we can see it all, and 10. Okay. You know how to do your Windows
Yeah.
setting? You hit the window button and then you put it in? Yeah, okay. Then you can hit graph and see it.
There's a little bit, like just time. Yeah,
Or you just put it into the zone.
oh, it's supposed to be straight.
Okay, well, let's just, I won't worry about seeing it because I think that I forgot how to do one thing. I always forgot how to do that. Anyways, our point that we really want is to hit the stat button again. Okay, arrow over to calc. So one arrow over to calc. Press enter. Arrow down to number 4, linear regression, AX plus B. Hit enter. And then it should say, like X and is L1 and Y is L2. Or it might just be default. And then arrow down, press enter or calculate. Okay? So you should get something that looks like this.
That's what I got.
Yes, you got that? You get something that looks like that? Can you see it in the thing?
Yeah.
A little bit lower.
Yeah.
Yeah, just wait, I'll focus. Okay, there you go.
Okay. So, this shows us, it says, it's giving it a little bit different. What's the only difference? It's representing it as y equals ax plus b, right? And then it tells us what a is and what b is. So it says a is equal to, what is it, like 7.439? And then it tells us b is equal to 0.3726. Okay. Oh, and I guess we should answer the actual question of what we did. So since VF is proportional to the square root of D, then we set x is equal to the square root of D. Okay. So now this is nice because, and it should make, if we found the plot, which there was one trick about making the plot that I just kind of forget about how to do right now, but I will show you in a bit. So this is like meters squared, right? Like the square root of, not meters squared, the square root of meters, so to the power of a half, same thing. So you should get like a linear plot. But the cool thing with what we just did was that, I don't know what, I think that it's drawing something different. I'll fix that in just a minute after I do this, yeah. It's giving, what's cool is that we didn't have to have graph paper and plot it out, right? That's a plus, right? And we didn't have to go find 2 points and go y2 minus y1, blah, blah, blah. Because look, what is that? That's our slope. So you can just put the data into your calculator and make it do the work, and you get that. It's the same, you end up with the same results, right? But you maybe just have to do a little bit less work, right? So that's nice, and you can do that, because you get your graphing calculator all the time, for every test, everything, right? So that's a technique that is helpful. So let's move on to the next question then, and see if we can use what we just figured out. What does the slope of the linear graph represent? Okay, so that means we have to try, this is when we think we need to fit our VF is equal to the square root of 2AD into our y equals mx plus b formula to figure out which one is the m. Okay? So, we know that this is our y. Y is equal to, and I'm going to rewrite, well, what is my x? Do I know? X we said is equal to, what did we just say? Square root of d. So, I'm going to go square root of d. I know that's an x. So here, it's my y. Here is the x. What is left over? Times the square root of 2a. Right? That's everything that's left over. If I broke that chunk into this and this means the same as this and this. You agree? Yeah. So this is my m. Traditionally, we would write it y equals mx plus b, so we could rewrite it if we want to. So we could say VF is equal to square root of 2a times by square root of d. So our answer then, what does slope of the linear graph represent? Slope is equal to the square root of 2a, because that's what I just said right here, right? If that's what's left over, because was anything added or subtracted? No. I already identified my y, I identified my x, everything left over is the slope. Okay, that was what was left over. So my slope, I can conclude, is 2a. Now, here's the exciting part. Look, slope is equal to 2a. I'm just going to write that here. Slope is equal, or square root of 2a. What did I just say back here? Slope is equal to that. Slope. Right? Huh? So now, there's two places. Slope equaled a number, and slope equaled variables. I can make them equal to each other now. So I said slope is equal to 2a, and in the other part, slope was equal to 7.439. Yes? And look what the question's asking me. What's the acceleration of the rocket? What? I can totally figure that out, right? So equal these to each other now. So now 7.439 is equal to the square root of 2a. And you are solving for a. Okay, so you want, yeah, so you square each side to get rid of this and this. So now we have 7.439 squared is equal to 2a. So divide this by 2 to get your a. And what do you get? 27.6 blah blah blah. Okay. 27.6709. And so we have our sigdigs. If we go back to the beginning, in our data that we are given, so when you're wondering about sigdigs, you go back to the data. Whatever the data sigdigs are, that's what your sigdigs are. So how many? 2. Yeah, 2 is the smallest amount. So 28. And what units are what units are acceleration in?
Meters per second squared.
Squared, yes. We would have seen that if I would have applied all of the units to the whole thing, but I guess I was lazy and I didn't, so my